so to find our pH from our H plus concentration, we take minus the log. Okay, and I have 4.82. pOH, I took 14 minus my pH value. And I end up with 9.18. And then for OH minus, because I know the pOH, what I did was the OH minus is equal to 10 to the minus pOH. And this is basically the anti-log. So if minus the log of OH minus equals my pOH, if I do 10, power of 10, I'll get this answer. So I ended up with 6.7 times 10 to the minus 10 molar. Okay. So when you're calculating pH and looking at concentrations, there's a good sort of sanity check you can do. When the pH is, in this case, was around 9, I should end up with an exponent of minus 9, minus 10, somewhere in that range, because that exponent is basically showing up here before the decimal place in the pH, or pOH. Okay, so I'm not going to go through in detail on these others, but I'll write them out for you. So my H plus concentration when the pH is 11.51 is 3.1 times 10 to the minus 12. And that makes sense. That's a really small concentration. The pH is really high, meaning that it's a very basic solution, so there shouldn't be a lot of H plus in solution. OH minus, I have 3.2 times 10 to the minus 3 molar. Again, very basic solution, should have a high OH minus concentration, and that's fairly high. Take the minus log of that to calculate the pOH, and I get 2.49. Questions on any of that? Yes? On this side, the 10 to the minus. Did I calculate it wrong? Is that, or did it, okay. So basically explain this. Is that what you're asking? Okay, so it's derived from this expression. In order to get rid of the log, we'll do 10 to the minus. So you take 10, I don't know how to say that properly. What do I say? Excuse me. This will get rid of the log on both sides. So you end up with OH minus equals 10 to the minus pOH. So other thing I did here is move my negative sign over without telling you. Does that help at all? Okay. I'm really bad at explaining the math part. Yes, sorry about that.
Why is there 3 sig figs for pH?
3 sig figs for pH. Oh, there's only 2. So the first, before the decimal place doesn't count. These are the only 2 that matter.
Okay, got it.
Yep. Anything else? Good questions? Yeah.
Is there a special way you need to type that into your calculator? Because when I type 10 for negative, it's 9.8. I get 1.5.
Yeah, parentheses might help. It depends on the calculator too.
Okay. Whatever you do with parentheses.
And it also, make sure you're using the E. That might help too. Yeah. Because otherwise it might be multiplying. So if you do, for your concentration, would do like 1.5 E minus 5, as opposed to 10 to the minus 5 times 10 to the minus 5. That helps too. Cool. All right. Okay, so now we're going to actually start adding acids and bases to water to make aqueous solutions. What I want to do first is think about essentially, we're going to apply the Chateliers principle to our autoionization of water equation. So when we add, for instance, HCl to a solution, we know that HCl is a strong acid, so it completely ionizes, completely deprotonates to form H3O plus and Cl minus. Okay, so I don't necessarily want to worry about this equation, but I want you to see that addition of a strong acid or even weak acid is going to add H3O plus to the solution, or H plus. So if we add more H3O plus to our equation for the autoionization of water, which direction will the equilibrium shift in order to regain equilibrium? It's going to go to the reactant side. Okay? So if we add more H3O plus, we're going to shift back to the reactant side in order to regain equilibrium. What does that say for the OH minus concentration? What happens to it? It goes down, it decreases. What happens to the H3O plus concentration solely based on the autoionization of water? It also decreases, right? Now, it's separate in your mind autoionization of water equilibrium and the fact that we've actually added acid. Yes, in practicality, there is more H3O plus in solution, but none of that, less of that is coming from autoionization of water than if it's just water in solution. Okay, so here's our HCl. Again, we're going to put this in water. Reaction's going to go to completion. Actually, I'm going to skip ahead to this next slide. Sorry, it's the same thing. Instead of writing this one more time. Okay, so here's our reaction, addition of HCl to water. So if we start with 0.1 molar HCl, how much H3O plus is formed? So this is just a stoichiometry question because this reaction occurs to completion. So we have for every 1 HCl, we produce 1 H3O plus. So we'll end up with 0.1 molar H3O plus. Everyone okay with that? Okay. All right, but we also have the autoionization of water happening. That's our equilibrium. Okay? So how much H3O plus is contributing from the autoionization of water? Okay. So let's write this out. Let's write out our equilibrium that matters. It's H2O, 2H2O, in equilibrium with H3O plus OH minus. Oh, yeah, plus OH minus. In pure water, we know that the H3O plus concentration is 1 times 10 to the minus 7. But what happens if we add more of this? Like we just said, the concentration goes down. Yes?
So, like the reaction of HCl and water, it's not in equilibrium, but the reaction of ionization of water is?
Correct. Yeah, the first reaction up there, HCl and water, is not in equilibrium. Okay. The second reaction, the 2H2O, that's our equilibrium. That's the one that we're going to be thinking about for this problem right now. So we know that addition of a product is going to shift the equilibrium back to the reactant side. So from simply the autoionization of water, the concentration of H3O plus is going to be less than 1 times 10 to the minus 7 molar. Now we could go through and figure this out, okay? But we're just going to leave it at this, okay? Because once we know that it's really small, less than 1 times 10 to the minus 7, we know that the concentration of H3O plus from the strong acid, from HCl, is much greater in concentration than this 1 times 10 to the minus 7. So this autoionization of water, when you add a strong acid, is negligible. And as I said last time, the problems involving weak acids, strong acids, strong bases are typically easier to solve. This is one of the reasons why, okay? Because now we can ignore autoionization of water. We can ignore that equilibrium. Let's see. Okay, so our H3O plus concentration from the HCl is 0.1 molar. We know that H3O plus from the autoionization of water is less than 1 times 10 to the minus 7. So it's essentially, we can ignore it, negligible. Okay, so we can calculate the pH. pH is equal to minus the log of 0.1 from the HCl and equals 1. Okay. So what's the pOH? 13. So this is 14 minus 1 is 13. This can give us back our OH minus concentration. Yep.
How do you know like when something is negligible, like how big or small is the number considered negligible when you're considering this?
Yeah, so the question is, how do you know when you can ignore something in terms of size of its magnitude of its concentration? So I look at the two values that I'm comparing. So we have the 0.1 molar and the 1 times 10 to the minus 7 molar. 0.1 is huge in comparison, right? Let's do a quick demo of this. This is a fun calculation. What is the pH of 1 times 10 to the minus 8 molar HCl? What do you get? You get 8, right? Does that make sense? I mean, mathematically it makes sense. But it's an acid. And we know at 25 degrees Celsius, our Kw is 1 times 10 to the minus 14. Anything with a that's an acid is going to have a pH less than 7. So how does this happen? So this is a case where we can't ignore the autoionization of water. Now the concentration of H3O plus from autoionization is not negligible. Okay, and we would actually have to go through and account for that. We would probably find, we'd have to add the concentration of H3O plus from the acid and that from the ionization of water. It's a little bit more challenging of a problem. So really, if we're looking at a strong acid, anytime the concentration of that strong acid is between 1 times 10 to the minus 6 to 1 times 10 to the minus 8, you can't ignore autoionization of water. However, that's not going to come up in this course. There is a homework problem that asks you to calculate the pH of HCl at 1 times 10 to the minus 8 molar. I was going to assign it, but then it actually asked you to like type an explanation as to what's happening. And I thought that sounded tedious and annoying, so I didn't assign it. But this is the cool thing that happens with really dilute strong acids. So, good question. Does that help though? Yeah. So compare this concentration and this concentration. Significant figure-wise, if this was 1 times 10 to the minus 3, we might even be able to ignore it. But I mean, it's never going to be like that.
I think I'm just confused because we had talked about like negligible, like ignoring stuff previously.
Yeah, we're gonna.
There was
We're gonna come back to that. Yep,
Yeah.
we'll come back to that. That'll be the case where it matters. So here you can pretty much ignore autoionization of water for a strong acid. Okay. Any other questions on that? Okay. So here's another problem. I'm going to have you guys work on this. So we have barium hydroxide. Has a solubility of 0.1077 moles per liter at 25 Celsius. If we add that many moles of barium hydroxide and dissolve it in 1 liter of water, so it completely dissolves, we make a saturated solution. Let's calculate the pH and the OH minus concentration for that solution. Okay? The pH to be higher or lower? Slightly lower? I agree with that. Okay? Okay, so in doing this calculation, the only thing that's going to change is the volume that you're dividing your moles by, right? So I end up with an OH minus concentration. I'll let you guys work this all out. You can check my math again. Equals 0.144 molar. My POH is 0.843, and my pH 13.157. Okay, so the pH did lower slightly. Questions on that? Okay. How do you guys feel about pH? POH? Good? Okay. I'm going to skip ahead. We'll do this. Here's a couple of slides here. I'll go ahead and write the answers, and you can make sure you come up with them. That's that one, 3. 1 times 10 to the minus 7. So looking for, in this problem, hydrogen ion concentration, you should get 3.1 times 10 to the minus 7 molar with 2 sig figs. Okay. There's some, OH minus concentration, when you're given a concentration, you're given a concentration of OH minus, what is the pH? I end up with 10.18. This one's a little fun. Maybe let's do this one. Yeah, let's do this one. Okay, so let's calculate the pH of a mixture formed by adding 50 milliliters of 0.02 molar HCl to 125 milliliters of 0.01 molar HI. Okay. What do we know about these two acids? They're both strong acids. Okay. All right, I'm gonna, for the sake of time, kind of move us along here. So, for both of these acids, because we're mixing them together in one solution, they're both strong acids. Essentially, the concentrations are going to be additive because the concentration of H3O plus is going to be based on the number of moles of each of these things added. So from HCl and from HI, we're going to calculate the moles. And in order to do that, we're going to take our concentration, multiply it by the volume of that substance that was added. So we had 0.02 molar HCl and 50 milliliters of that. And so we end up with 1 times 10 to the minus 3 moles. And I'm also, because HCl and HI for every one molecule of that acid, we produce 1 H3O plus. We can say that the number of moles is equal to H3O plus fairly readily. If you wanted to write it all out and do the stoichiometry, you're welcome to. moles of H3O plus from HI. Again, the 0.01 moles per liter times the 0.125 liters. We're going to end up with 1.25 times 10 to the minus 3 moles. And now we can add these together. And we'll get 2.25 times 10 to the minus 3 moles in total of H3O plus. And in order to find the concentration, we divide by the total volume, which was 175 milliliters. Okay, which is 0.175 liters. Okay, so I end up with a total concentration of H3O plus of 0.0129 molar. And pH is equal to minus the log, which I end up with 1.889. I don't think that one is significant at the bottom there. The 9 is not. Questions on that? Okay. So if you have strong acid, strong base, you're mixing two of them, just worry about the H3O plus or worry about OH minus. Okay. All right, so now we're really going to start to get into the equilibria involving weak acids and weak bases. When we put a weak acid in solution, we are going to form H3O plus and its conjugate base. Okay, so weak acid will react with water to form H3O plus and conjugate base. It's the same thing essentially as a strong acid, except in this case, we're not going to completely react. Okay? With weak bases, we're going to form OH minus and the conjugate acid. Okay? Ionization does not occur completely. All right, so we're going to have our equilibrium arrows, and with that, we're going to have to use ice tables if we want to figure out equilibrium concentrations. So the problems get a lot more interesting. Okay, so can we see? Okay, here is a weak acid, HF, hydrofluoric acid. This one's often confused for a strong acid simply because it kind of looks like the others, but this is a weak acid. This is the acid that was used in the first episode of Breaking Bad to dissolve the guy in the bathtub? Yeah, okay. So, weak acid, surprisingly. When we write our K expression, we're going to use K sub A. Okay, the A is going to signify that it's a weak acid. All right, and it's the same as we've done a number of times now. Products, concentration of products over reactants. And in this case, the only reactant that's going to matter, it will be the weak acid. Water will not play a role, it's a liquid. So in this case, Ka is equal to concentration of F minus times H3O plus divided by HF. Okay? And we'll find that all of our weak acids are going to have a Ka value. This one is 6.8 times 10 to the minus 4. The other thing that you might see come up, I think there might be one, maybe two homework problems, and I think we looked at an example in class last time, for just a very generic acid formula. So sometimes it's easier just to assume that every monoprotic weak acid, no matter its actual structure, is simply HA. And when you put it in solution, you'll end up with H plus plus A minus. So if you see something like this, this is just a very generic formula. Okay? You could write a Ka for this. A minus is the conjugate base of whatever weak acid HA is standing in for. Okay, so this is a table with a number of different weak acids and their Ka values. Okay, so chlorous acid has a Ka of 1 times 10 to the minus 2 molar, or sorry, 1 times 10 to the minus 2. Someone asked about HCl last time, and it wasn't on my list of strong acids. In your book, it is a strong acid. It is not the same in every textbook. That is one that's sort of on the line of strong, weak, okay? But in your book, it's a strong acid, so therefore it is a strong acid in this class, yes.
Why is it like on that like intermediate stage?
Yeah, so the structure of these acids plays a role in its acidity. I would say that there's a continuum. And whoever draws the line just drew it in a slightly different place. That's really all it is. So it's the Ka value for HCl is going to be larger than this 10 to the minus 2 value, which is basically almost 1. I mean, I don't know what the actual value is. I didn't get around to looking that up, but we could look it up and find out. Okay, so which of these acids then will dissociate the most? Which means which will have the greatest quantity of conjugate base? That'll be those at the top of the list. Okay, the ones with the largest Ka. And then, of course, those at the bottom of the list don't dissociate as much. They're going to have very small amounts of conjugate base in solution. This goes back to Ka being large or small, being product favored or reactant favored. And now these are all less than 1. Okay, so all of our weak acids are going to be favoring the reactant side, but now we're looking at the magnitude within that. Okay. Other thing to note here is that the acids with the highest pH have the highest Ka, largest Ka. And you could assume that because we know that the conjugate base is going to be larger in those acids with a larger Ka, concentration of conjugate base, so therefore the concentration of H3O plus will also be larger. For our weak bases, this is a weak base called urea. Okay. For this, we're going to use a base ionization constant K sub B. Again, it's just a K value that we're designating, saying this is for a base. Same sort of thing, products over reactants. So we'll have concentration of HNH2, CONH2 plus times OH minus divided by our urea NH2, CONH2. Okay, this is a Kb value of 1 times 10 to the minus 14. Not that you need to know those. These are all tabulated in your book. If you come across a problem and it seems like you should have a Ka value, for instance, you're given a weak acid or a weak base, or a weak acid or a base that is not on your list of strong acids or strong bases, it is most likely a weak acid or weak base. I've seen it before where homework will forget to put the Ka values, or they just don't put that in. These are tabulated, so find it in your book somewhere. It's not usually not going to be a problem that's just extremely hard. Okay. B.
Is it
Okay, so we'll start here next time.